When you think of the word hovercraft, a few things may come to mind. You may think of Aladdin's red carpet, or you may think of Marty McFly's hoverboard. Unfortunately, the first is not real, and the second, though a similar product can be built, is about $15,000 above our budget.
A year ago, we embarked on a journey with an open mind, but plenty of questions to be answered. We did not know where our lofty plans would take us, and we did not even know if our goal was attainable. Now, we will take you along our year-long journey. Welcome to Operation Amphibious Spartan.
Behind creating Operation Amphibious Spartan was to create a completely electric hovercraft that could traverse both land and water, hence the name Amphibious. Freshly inspired by our alternative energy projects, we set off with high hopes for success to use green power. We knew this would be a challenge because most hovercrafts today are powered by gasoline. Gasoline provides far more energy per unit of volume than electric. However, we wanted to create a renewable product that is unique to anything on the market today. Before we dive too deep into our journey, allow us to explain how the hovercraft works.
There are two major components to the functionality of a hovercraft. These are lift and propulsion. Lift is the upward force and propulsion is the forward motion creating force. Lift is obtained by forcing air into a flexible skirt on the underside of the hovercraft. As pressure builds inside of this skirt, it inflates and the hull of the hovercraft begins to rise. If we continue to pump air into the skirt though, the pressure would simply become too great and the skirt will pop, causing the hovercraft to come crashing down. To solve this problem and to allow the hovercraft to move properly, a hole is cut in the bottom of the skirt to allow a release of the air. Air naturally seeks to travel from high pressure to low pressure, so the high pressured air inside of the skirt will want to escape. As the air releases, a small space forms between the skirt and the ground, reducing friction immensely, causing the craft to hover or rather glide across the surface. The constant pumping of air into the skirt and the continuous release maintains this gliding properly. Unfortunately, it is slightly different than the traditional belief of hovering, because we only hover a fraction of an inch above the ground, though the hole appears to hover much higher due to the air-filled skirt.
We started our project by talking with the professionals. Members of our group went to meet with the owner of Lone Star Hovercraft, Benjamin King. We questioned King on the best ways to generate lift, what sort of materials work best, and a reasonable timeline for constructing our hovercraft. Fortunately, King was actively working on a custom project where he was building a hovercraft out of plywood. This helped us a lot in the planning of our hovercraft. King then proceeded to show us what a completed industrial-grade hovercraft looked like and answered many questions that we had.
With King's confirmation that it was possible to construct a hovercraft out of cheap materials, our team gathered at Cole's house to begin brainstorming on the design. We reviewed the project financially and then began researching all of the parts that we knew we would for sure need throughout the construction of our hovercraft. It was at Cole's house that night that we created our very first model hovercraft out of a plastic bag, paper plate, and straw.
After hours of online shopping for reasonably priced materials, we took our first of many shopping trips to Home Depot. We bought 3 16th-inch thick plywood for our frame and 3 2-inch foam boards for insulation and flotation. In addition to the materials that we were going to use for our base, we also bought fiberglass duct tape, which it was advertised to be 10 times stronger than duct tape, and this tape was very useful and a great investment. And we began to look at corded electric leaf blowers. We chose to go corded because they had a much higher CFM, or cubic feet per minute, output than other leaf blowers, and were significantly cheaper than our other options.
Throughout the next few weeks, we ordered 3 corded electric leaf blowers and anxiously awaited their arrival. While awaiting the arrival of the leaf blowers, we continued to research and conceptualize the most effective way to generate lift with the materials we were planning on using. For our very first step towards physical construction of the hovercraft, we glued 3 2-inch pieces of foam together. And then on top of that, we glued the 3 16th-inch piece of plywood. We used solvent-free Gorilla Glue so that we would not accidentally dissolve the foam base, which would be really bad.
The next weekend we gathered back together to observe how well the foam and plywood glued together. The bond was a success. Our next big step in the construction was to strengthen the structure and preventing insects from crawling into the seams between the foam and the plywood. In order to do this, we sealed the entire perimeter of the hovercraft with duct tape. We then began to conceptualize the best places to drill the holes to stick the leaf blowers in and how to attach the skirt. We went online shopping again, which at this point was becoming a hobby, for a skirt and circular drill bits that could be used to make the hole through the foam and the plywood.
The skirt is the material that inflates when the leaf blowers turn on to generate lift. The best material that we found for us to use was an industrial-grade heavy-duty shower curtain. It fit our allotted budget and is very durable. We bought 2 shower curtains and affixed them together with duct tape. This made a material that is just large enough to cover the bottom of the craft and wrap around the borders.
We decided that a circular hole saw with a 5-inch diameter was the perfect fit to make the holes for our leaf blowers. On November 2nd, we gathered together in Cole's garage to make our first cut into the hovercraft frame. This was the point of no return. We decided to make the cuts on opposite sides of the frame towards the middle because that way the air released by the leaf blowers could be dispersed evenly in the skirt. We were a bit worried before we got started about messing up because there would be no going back, but we closed our eyes, said a prayer, then began cutting into the wood. Everything went very smoothly and we created both of the holes for our leaf blower without an issue. After cutting into the wood, we cut the foam out separately, therefore creating a hole for the air from the leaf blower to travel unrestricted with the craft to fill the skirt.
Our next step was to attach the skirt to the hovercraft frame. We spread out the skirt on Cole's driveway and placed the hovercraft directly in the middle of the skirt. We then took measurements and connected the skirt. We overlapped the skirt onto the hovercraft 3 inches and folded hospital corners. And now it is time for test number 1. With the skirt attached, we inserted the leaf blowers into the holes and plugged them into a wall outlet. We turned them on and watched as our skirt inflated and remained inflated until we turned the leaf blowers off. It was a success. The test proved to us that the shower curtain worked as a skirt and that the way we folded and taped the hovercraft together was efficient.
A couple weeks later, on November 28th, we finally gathered the confidence to cut the hole into the skirt. We decided to start small and then stop cutting to test out to see if it hovers, and if not, keep cutting. We started out with a circular hole 2 feet in diameter. That barely got us off the ground and was fairly unreliable. The air would escape out of the hole in the middle, but then get trapped by the skirt that was pressed down by gravity, resulting in a very bumpy ride. We then decided that we needed some more surface area with air escaping, so we began to cut an oval shape instead of circles. We would cut a little bit more than test it out. We settled for a horizontal diameter of 3 feet and a vertical diameter of 6 feet. The hovercraft lifted off the ground and stayed elevated. The craft hovered very smoothly in contrast to when the hole was smaller.
As we tested more and more with inflation, we noticed that as the skirt deflated, the tape border would release, damaging the airtight seal. To solve this problem, we drilled into the wood lining around the tape border to improve the strength as well as add an improved aesthetic. While we were drilling into the frame, we decided that we needed to find a way to hold the leaf blowers in place while they were running. To do this, we attached drainage tubing to the craft hole and expanded the tube so that the leaf blowers can easily slip in and out. With the leaf blowers inserted into the tubing, a semi-airtight seal is created so that the leaf blowers can provide efficient lift.
Now that we have achieved hovering with external power, we needed to make our craft completely autonomous. The largest challenge that we faced is that our planned battery source, a car or marine battery, ran in direct current and the leaf blowers ran in alternating current. In order to provide power for our leaf blowers, we needed to use power converters, which take the DC current and output AC current. After testing multiple inverters, none of them seemed to work, and we were really confused. After hours spent online, we were still stumped, so we went to electrical parts outlet. When we went into the store, we were informed that the wattage of our inverter is much too low to provide power for both of our leaf blowers. In simplicity, wattage refers to the rate of power output necessary to power a motor, and the inverters that we had were unable to provide the power output necessary. EPO suggested that we purchase a very high power inverter, however the part was very expensive and was way over our budget. Essentially, we were stuck.
A week later, we found the solution to our problem. Rather than only having one battery and a single inverter to power our leaf blowers, we will have multiple batteries and multiple inverters. This solution will increase our weight. However, having the extra batteries will also increase our maximum runtime.
The next step to achieve complete self-powering was to find a storage compartment to store the batteries, inverters, and cords. After thorough discussion, we decided to find a double use for this storage compartment. After going to Academy, we found that we can use a heavy-duty trunk as a seat to hold our batteries, inverters, and cords. The heavy-duty plastic trunk greatly reduced the weight we originally anticipated because the plastic is much lighter than the plywood seat we originally planned to build. After purchasing the trunk and confirming that the batteries will fit, we cut holes in the sides and rear side of the box to allow for the small extension cords to pass through and to provide minor airflow to help cool the system if necessary.
The next major step that we faced was our means of propulsion. We tested several different types of fans, but none of them seemed to work. We tested for many weeks with no success. Eventually, we discovered that the fans we were testing put out a very high CFM, or a large volume of air. However, we needed fast-moving air. Since we had a third leaf blower, we decided to try something new. The leaf blower fan motor spins at an incredibly high rate, and if we could remove the motor and attach a larger fan blade, the fan just may work. One evening, we got together and carefully disassembled the leaf blower to gain access to the motor. David and his dad, our mentor, then got to work.
Over the next few days, David and his dad worked on making a fully functioning fan that has the ability to rotate and steer our craft. The first step was to attach a fan blade, and after a few attempts, it was successful. Using a combination of plywood, PVC pipe, wire, and a variety of other materials, they created a safe and sturdy housing for the fan and motor, as well as an easy method to attach the fan to the hull of our craft. Once attached to our craft, the fan did exactly what we planned it would. The fan does provide a slight amount of propulsion, completing our goal.
Looking back on the year-long journey that we have traveled on, we are very proud of what we have accomplished and thankful for what we have learned. Though the hovercraft didn't quite come out exactly as we had originally hoped, we still consider the project a huge success. After reflecting on the project, we found that our goal of only using electric power is a large limiting factor to our design. The hovercraft does not move as fast as we hoped, and that is because we do not have the means of purchasing a large enough fan or motor. Over a certain power, the prices of electric motors increase exponentially, and we do not have the ability to purchase a motor at that high price.
In conclusion, we are very thankful for the opportunity to embark on such a journey. We have learned countless life lessons such as communication, planning, organization, and time management. It is these lessons that we will be able to take with us to college and beyond. Finally, we would like to thank everyone who has helped us along the way. We would like to thank Mr. Avis and Mr. Barrett for the opportunity to be in this class and the guidance that you have provided us along the way. We would like to thank our parents, especially Mr. Kamitsky, who came to our rescue in multiple situations and helped us when we were completely lost, as well as Mr. and Mrs. Oliphant for having an open door whenever we needed to work on the project and for letting us take over your garage for the last 9 months. And finally, to the juniors, best of luck to you as you embark on your own journey, because it will truly be over before you know it.